Ji, Assalamu alaikum. In the last short video, I discussed with you the one of the non-isolated version of the switching power supply, which was a buck converter. So in the buck converter, we saw that the output voltage is always less than the input voltage. In today's lecture, I want to discuss with you a topology which is also an isolated version. However, the output voltage is always greater than the input voltage, and this is called the boost topology or boost converter. The boost converter basically consists of an input capacitor, series inductor, and then output diode, and then output capacitor, and switch or MOSFET is connected in between the inductor and the diode anode side, and the other point is connected to the common ground. Boost converter can be operated in basically two configurations. One is called the discontinuous conduction mode, and other is called the continuous conduction mode. In discontinuous conduction mode, all the energy of the inductor is transferred to the output side or the load side within a switching cycle, and the next cycle starts from the fresh. Whereas in the continuous conduction mode, although in a switching cycle the energy is transferred to the output, but still there is some energy remaining in the inductor that adds to the next switching cycle. We normally avoid operating the boost converter in the continuous conduction mode because we regulate the output voltage using a control loop. And as an example, suppose that the output voltage is decreased due to the heavy current demand, or in other words, the load is increased. So in order to replenish the charge of the output capacitor and the load, the boost converter increases the on time of the inductor. In this phase, the inductor is charged so that when the switch or MOSFET is off, this energy should be transferred to the output side through diode. But because we have increased the on time of the inductor charging, so less time has remained in the off time of the inductor when this energy is transferred to the output. So in other words, in order to maintain the voltage to nominal value, which was decreased previously due to the heavy load demand, the charge transfer time has been reduced, so a reverse effect has been generated. In the transfer function case, we say that right half plane 0 has been created. So whereas this effect is not generated or caused in the discontinuous conduction mode, because all of the energy is transferred to the output within a switching cycle. As long as the components values calculation is concerned, the inductor in boost converter is calculated at the minimum input voltage range. That is because the peak current which is used to select or design the inductor consists of two parts: AC component and the DC component of the inductor. The DC component and as compared to AC component is large, because and the AC component is maximum at the 50% duty ratio, and not at the Vin maximum or Vin minimum. But as I told you that the DC component is the large component, so we neglect the AC component, and the DC component is large at the minimum input voltage range. So we slide the inductor at the minimum input voltage. Similarly, the MOSFET or the switch is selected also as the minimum input voltage range, because at the minimum input voltage range a lot of current flow through the MOSFET, and hence the RMS current rating also maximum at the input minimum input voltage range. The output capacitor is also selected at the minimum input voltage range. As long as the input capacitor is concerned, it is calculated at that value of the input voltage at which the duty ratio is 50%. So concluding, boost converter is used to step up the input voltage, and we use the boost converter where the output demand is that the output voltage should be higher than the input voltage. And the different components selection is quite different from the buck converter. So this was a today's short video. So stay connected, and thank you very much.